Okay, let's get cracking then. Hello, everyone, and welcome to the City Data Science Society. We have an event today that's been produced in collaboration with Daniel Sikar, who is a master's student at the university. So he's made a workshop on how we can detect fire with artificial intelligence, which is going to be really interesting. And feel free to ask questions throughout the session. This is really interactive. If you don't get anything, just type it in the chat, or you can put your mic on and talk to us as well. I'm going to put the link to the Society website in the chat here. If you want to join up and get information about our next events, then you can do so there. But without further ado, I'll hand over to Daniel and we'll get cracking. So if everyone else that's on the committee could just turn off their cameras, we'll get going.
Hi everyone. I am Daniel, and here. Oops. Sorry, I'm back. Just need to get that computer vision workshop link up. Cool. So it should be now this guy. Share. Right. We've sent a link around to this City Data Science Society computer vision workshops on GitHub. And so let's stop for a minute just to make sure that everyone else can actually access this link. So the address then would be github.com, City Data Science Society. And then I'm just going to post this link here on the chat. So
I've done it. Don't worry, Daniel.
Cool. Perfect. So let's give it another few moments so everyone who wishes to do so can connect or open this in a browser. And meanwhile, to the ones who are here, if it's possible, could we have a quick show of hands? The people who are coding in Python already, who have have some programming experience and have coded with Python. Cool. Ben has, Marina has, Ben Hinge has. Cool. All right. So it's not essential, but it's just to know, just so we know at what level we're working, because obviously we want to make this accessible to everyone. And then next question is, if you have worked with Jupyter Notebooks, so this platform web browser based called Jupyter Notebooks, could you have a short hand again? Okay, so Chikazi has, and Marina has. Cool. All right. So, right. Let's head off then. And if anyone else joins, could I ask Maxim to kind of, or we'll have to play it by ear and try to go over this link again. But on this page, we have this Jupyter Notebooks section. And we have a how to detect fire with AI open in Google Colab. Before we head that way, I'm just going to this previous page just to show what we're aiming to go over today. So how to detect fire with AI. This thing called AI, artificial intelligence, become a synonym for this little thing. And you say, oh, there's an AI to do something or other. So this AI, which is this little thing, like an engine, it detects fire. So we see here two images. It's an oven lighter, and one, the lighter is lit, there's fire. The other one, the lighter is not lit, there's no fire. So there are two classes here, basically. It's fire and no fire. So what we're doing is we're training a convolutional neural network for a computer vision binary classification task. And this is something that when you start reading articles about this, you'll see this term popping up a lot. It's a binary classification task because we're classifying between two classes. We're trying to distinguish between these two classes. So binary. And in some cases, you might be trying to distinguish between hundreds of classes, like, well, anyway. So this would be the simplest case then of a classification task, a binary classification task. So heading over to the notebook, I'm going to click this link here, open in Colab, in this section, how to detect fire with AI. And then next thing, I land in the Google Cloud, because that's where this thing is being hosted, and in Colab, so collaboratory. And we know that because it's this icon here. So is everyone on this page now? Could we have a show of hands? If you're interested in following the practical side of it. If you don't want to follow the practical side of it, or if you haven't got to, you do, but you haven't got to, we can wait a bit more. If you're interested in running the actual lab. What have we got here? Colab link code. All right. So what we have here is this environment called Jupyter Notebooks, and it basically is in a browser. And what we have what is called a cell. So here we have a text cell, and it's like text. And here we have a code cell, which is code. So if we want to run the code, there's this play button here, and we can run the cell, Control Enter to run the cell, and it says cell has not been executed in this session. So I'm going to run this cell by clicking that, and if whoever is following could do the same. It's going to say, oh, this wasn't authored by Google, and I'm going to run anyway. And then, all being well, so what this code is trying to do is it's trying to download some data onto the Google Cloud, but Google says, well, we're going to have to authorize this, make sure you are who you are. You know? So this link appears. So we'll have to click on this link, which will take us to a page. And then once we get to that page, you have to choose an account and to continue with the Google Cloud SDK. If you haven't got a Google account, which is not an email account, you would have to register at this point. So sign in with Google and complete this verification that way. So in my case, I'll choose my city account. I'm going to allow, and then Google is going to give me a sign-in code, which is here. Right, that's a complicated bit. If you got this far, you definitely get to the end. So let's make some time to make sure that whoever wants to follow the practical part, your local browser. Oh, Ben, yeah, Ben's there. Ben Frost, Ben Hinge, did you get there okay? Cool. Anyone else following the practical part that would like to some more time to get to this page?
I'm sorry, which link were we supposed to follow? Because I was just setting up my monitors.
Okay, no worries. So, Marina, I'm going to head back to the. I'm going to head back a few pages, and where were we? Oops. Right. So we started. We were on this cell. Marina, did you get that far from the how to detect fire with AI? Then click this play button here on the left.
Oh, okay.
So once that's been spinning for a while, you should get, if you scroll down, you should get this link here.
Okay.
And once you click that link, that's when you have to go through all the verification.
Okay, I'm at the sign-in page, and then we copy that code and
so cool.
okay.
So now we paste that code in this box here. So enter verification code, and I swear this is the hardest part of the whole thing. After this, it's plain sailing, honestly.
Okay.
Anyone else is stuck on this bit but would like to join? We'll wait, you know, because this is the bit that's hard to get over. Once you get over this, you'll be running notebooks for the rest of your life. Honest, so if you wish to do so, of course. So this is the stumbling block. So Shikazi, if you want more time to, or if you're there already, but if you, and Eleanor, you know, what you guys want to do? Do you want to get through this bit and do the practical?
I think let's push on with the notebook, and then if they want to, yeah.
Cool. So I'm going to press return here, and that's it. We're in. Now, cool. So if everyone press return and let this code run, this thing's going to carry on spinning. While it spins, I'll explain what it's doing. So it's saying pip install iDrive, and it's preceded by an exclamation mark. So it's saying here in this environment where we're running on the Google Cloud, install this Python module called PyDrive. Then it's going to install a bunch of modules, and then it's going to verify and then create and allow us to write to that drive. And I've created a shareable link for the data. And here are the instructions if you wish to do so in future. You extract the shareable link from Google Drive, you paste it in here, and you say, well, we're going to create a file, and the file we're going to create is called datasets.tar.gz, and that's a compression format. So basically this is saying this is compressed data. So then if we move on to the next cell, so if you click on this cell such that this play button appears, what I'm going to do is run a list command. So we'll run, hello Sophie, we're like on the second cell already, but you should be able to pick it up from here, no problem, or at least follow it. So if we run this play button, and please do so, Ben Hinge and everyone else. This is what we'll see listed. So is everyone seeing the same thing listed? ADs.json datasets, could we have a show of hands there to make sure that we've got those items listed when you do exclamation mark dot ls? So basically, when you press this play button next to ls. Hello?
Working for me, yep.
Cool. All right, I'm going to assume it's working. So now we're going to move on to the next one. So we're saying we want to decompress this. So what we're going to say, so this is all running on a virtual machine now. We're running a command on a virtual machine. So we're saying, right, run this command, exclamation mark, xvf, so expand verbose, show me the files you're expanding of datasets.gz. So we'll press the play button here, and all being well, what's going to appear is a long list of files. So recapping, we've downloaded the file, we listed, we saw that the file is listed, and then now we're saying, okay, decompress that file. And so that's finished, and we have a bunch of files now on our file system. I'm going to close the cell now because it takes up a lot of space. So I'm just hovering over here, get this X mark, I'll close that, and we're back to this. So just to go over this exclamation mark thing, this goes back to Linux and Unix, so it's the birth of Unix. And if we then went to say, show me the manual for this tar thing, for this tar utility, I'd say exclamation mark tar, and it would say, oops, play button, and it would say, no entry manual for tar, right? There's no documentation. But if we said, for instance, show me the manual for the list, the ls command, it then would say, okay, we have a manual for this, and if you wish to run it, you want some more information about what it's doing, here it is. Go. So I'm going to comment this line back in again, get rid of that line. So what's happening now is the state we're in is we've downloaded the data and we've decompressed it. Cool. So now we are going to list these files to see, okay, we've downloaded this data. What have we got here? And I'm going to run 3 commands in turn. So we see that these commands are again preceded by exclamation marks. We're working on this Google Colab environment, running a Jupyter notebook. We're running this cell now, play button, and it says, right, for the first command, I said list and give me a list in human readable format. That's it, the file size on disk of dataset. And it says the file size on disk of datasets is 16K. The next one I run is I say list datasets fire. So list me everything that's in that directory and pipe that into another command. And this is very typical of Linux systems, Unix systems in general, is your pipe from one command to another. So I'm saying, in addition, well, you get me this list, and you send it to another command, which is a word count. And then at home or later, if you're interested, you could do an exclamation mark WC, and it would show you what this word count is about. And in this case, I'm saying, give me a count of lines, and it says there are about 12,000 lines in datasets fire. And then it says, oh, no, sorry, there are about 176 lines. So there are 176 files in fire, and there are 96 files in no fire. That's what these 3 things are telling us. Cool, let's move on to the next one. So here we're going to set a data directory and category labels to the actual algorithm that's going to work out this, that's going to be trained and work out this classification problem. So we'll say we want to create one variable called data directory, or data directory short form, for data sets. And then another one, it's going to be a list. It contains 2 entries. One's going to be no fire, one's going to be fire, and that's going to be in categories. So then I'm going to say, this is Python now. It's not we're not using shell commands. And we can tell that because these ones are not preceded by the exclamation mark. And I'm saying, well, show me the data type of data directory, the data type of categories. Tell me what is the category in index 0, what is the category in index 1, and print the type of category index 1. So this goes on to say, well, the data type of directory is string, the data type, of data directory is string, the data type of categories is list, the category list index 0 is no fire, the category list index 1 is fire, and the type of category index 1 is string. So that's just for us to get an idea of what these Python variables are. So now we have these variables called data category, and we move on to this section. We're going to import a bunch of Python modules, so the operating system module, the computer vision module, the numerical Python module, and this module that does the progress bar. So further down the notebook, when we're running the notebook, it will tell us, oh, this is how long how far you're into your job from 0 to 100%. So if you now run this cell, everyone who's following the practical part, it will, what will it do? It's going to create, it says, I want a plot size of 200. I want you to read this image that's on disk. So datasets fire and this image name. I want you to read it with this CV2 library. It's got a method called imRead, image read, and assign it to this imFire. And then resize the image to the size of the plot, which is going to be 200. So basically what we're doing here is resizing that image, 200 by 200. We're saying print fire, which is a label, and we're saying CV2 for imShow image fire. And the CV2 is a Google library, by the way, and it has to do with how things run on Jupyter notebooks. Normally, if you were running at home, you might be running cv2.imageshow, but in this case, this is the one we use. We do the same thing again for NoFire, and this is what we get. So the resized images 100 by 100 plus these labels we printed. So this convinces us, hopefully, that that's what we have on disk. It's all there sitting on your local disk on the Google Cloud. So Ben, all good? Ben Hinge? You're following, right? Can we have a show of hands? Yeah, cool. And who else is following? Marina, all good?
Yes.
Cool. All right. So moving on to the next section, what we're going to do now is create a training data function. So what this is doing is say, I want to create, I want to define a function that's called, and you call it whatever you like, it's called create training data. I'm going to, the parameters this function takes are an image size, a data directory, and a category, and categories. So now this probably rings a bell. An image size, what we defined previously, like as 200. So this is something we might add to this bit. A data directory, we have to tell it what data directory we want to, we're working with, and which categories we're working with. So there's some there's some comments here as to what this function is doing, but basically that's exactly it. It wants to know what image size we're dealing with, where the data is, what categories we have. And then it's going to iterate, it creates an empty list called training data. And then it says for category and categories, we know what those are. It's fire and no fire. It says join the data directory plus the category we're getting from here. So here, it's going to go twice through this loop. The first time around, it's going to get fire. The second time around, it's going to get no fire. And then it says the class number is going to be the index of categories at this point through the loop. So in this case, it's going to pick up a 0 and say, okay, so I know now that 0 is fire. And the second time around, when it's going through the no fire directory, it's going to, this is going to be equal to 1. So it's going to say, okay, I know what's happening now. Class num equals 1. That's going to be the no fire. And then it goes through the entire directory and it appends the image to an image array. And then it resizes the image and appends that to a training data. Oh, sorry, this is where the actual append is doing. It's appending these image arrays to this training data array. We'll see what that looks like further down. And there's also a try except, like a try block where that deals with exception handling. So if anything went wrong here, it would then at least we'd have an error message in this variable e, which would we'd be able to print and have a look at what it's, you know, what the error was about and carry on. So that's all this is doing. If we just click play on this one, what all that happens is we've created a function definition. Now we have this function in memory and we can work with it. So the next thing we do is, oh, just one more thing I wanted to point out is that we actually use the, where is it? Oh, LSTQM, where was it? This directory join. No, not here. Right. So here we are going to actually run that function now, and we define an image size of 64. And we say training data is going to be able to create, training data with a size of 64, and then the data directory that we defined and the categories we defined. So we press this play button, and all being well on your screens, you should see this progress bar. So that means that we're going through this function and we're passing it all the path to the directory where all our images are stored. So everyone, following can see these progress bars. Cool. Ben Hinge, all good? Cool. Marina, can you see that as well?
Yeah.
Cool. Perfect. Right. So now, oh, okay. Yeah. The bit I wanted to show you, which is interesting, if you get into, which I find interesting anyway, this, I think it's very interesting to have this kind of visual cue of what's going on that we got here. So in future, if you want to add this to your own applications, the bit that's actually doing that is on this line up here. So when it says for image in, so it wrapped this os.directory path. So it's saying for images in this path here, wrap it in this tqdm function. And when I run this code, it's going to pop up this progress bar. So that's the bit that's actually creating the progress bar. Okay, so now we have we're getting close to the most interesting bits. We now have our training data in a format that our neural network can actually process. So in this case, it will be as an array. So more about arrays very soon. But this cell, if we run this one, we'll have, it says we'll have a list of image arrays. And to convince ourselves that that is a training data with the labels, what we're going to do is say, from that training data that we created up here, so okay, fair enough. This training data says, run this function, assign the output to training data. And now what I'm doing here is I am using indexing to say, go to the 0th element of the training data list, because it's a list of arrays, and get me the first, okay, sorry, go to the 0th array of the list training data and get me the first element. So if we run this, it will say, okay, the element with index 1, and it's well, the element with index 1 in the 0th array is 0. So it's saying that the first training example, I'll use that expression, so we have a bunch of training examples here. The first label we have 0, which corresponds to no fire, as we can see in the image. So that's matching. And then we go on to say, right, now use this library, cv2 imshow, and show me the 0th array, show me the 0th index of the 0th array, which is the image. And then it picks up all those numbers, which is a 3-dimensional array. So it's an image, it's an RGB image. So it's a square image, and it has 3 channels per pixel. So every pixel in that image would have a red, a green, and a blue channel. And then the actual array is exactly that. It's a 3-dimensional array where every index of the array corresponds to a red, green, and blue quantity. And internally, this IMShow then gets every one of those quantities and plots it here and says, okay, so this one is very close to gray, this one's very close to black, that one's close to white, plots all this stuff. There you have your images that inside this array is represented as numbers. So, and in fact, if we just, I'm going to run another cell here. If we just pasted that and ran it like that, it would output a bunch of numbers. So there's the array. So we have here one index with the 3 RGB values, another index with the 3 RGB values, and so forth. So that's what this thing is doing. And okay, so we then go on to print, same again, but this time we say, now go to the 200th index of the training data list. So I want you to go to training data list, get me the 200th indexed array in that list. So it addresses this array by that index, and then it says, and then go and pick up the first well, index 1 of this 200th image array, and tell me what it is. And it says, right, that index is 1. So what that means is, sorry, the value stored in that index is 1. So it says, at this point of that list, we have this label 1, which corresponds to fire. And the date itself, here it is, it's a lit oven lighter. Cool. So moving on to, so has everyone got this far? I'll assume yes, yeah, because this is, so just to recap what we were doing here, we're trying to convince ourselves that that data set is actually here in this training data list. So the next bit we're going to look at is the, just have a look at, what's this about? Do I have to run this? Let me remind myself what this did. Yes. Now we run this cell because we want a feature and label in our training data. So what we're saying is get everything that's in training data, which is a list, and assign all the 0 indexes, which is the data, to our features, which is, this is now going to be an array, and assign everything that was in that index here. So assign everything that was here in that position. Sorry, I'm not explaining this very well, but basically what it's saying is this training data thing, everything that was held in the array part, which was the image, you put in features. Everything that was held in the label part, which produced this 0 and this 1, you put in label, and then keep appending it to it. So it says, I have now the shape of Y, which is my labels, and it says, well, I have 270 labels there, and then I say, well, print the shape of the first element of the X array, and it says the shape is 64 by 64 by 3, which is the side of our image. So what happened here then, there's one more thing we have to say. We have to reshape this because this has to do with how we need to pass the data to our convolutional neural network when we train. But I'm not going to go over this line here. It's just something that we need to keep in mind for future reference. Now, this bit is important. What's happening here is we're normalizing the data. So we have the pixel value, which you've seen up here. And these pixel values can be anything from 0 to 255. Now, what's happening here is we're dividing these values by 255. So we're putting everything in a range between 0 and 1. So we're normalizing the values, or pixel values. And the reason we do that is that it becomes easier to train a network with these smaller values. So just kind of quickly go over that. So because you'll see a lot of this when you're training convolutional neural networks, and when you're training networks in general, that it's good practice, well, in many cases, to normalize your data. So you're working within more constrained kind of numerical values, let's say. So here, we're actually going to create, it's a code that creates a convolutional neural network. And before we go over the code, I'm going to hand it over to Nick, who's going to give us an overview of CNNs. So this thing called the convolutional neural network. Over to you, Nick.
Thank you very much, Daniel. Hello, everyone. Can you hear me?
Yep, sound good?
Okay, perfect. Hello, my name is Nick. I'm the finance officer of the City Data Society. You probably have seen me in some previous webinars that we have here in the society. Thanks a lot, Daniel, for the really nice workshop. I believe that everyone find it as useful as I do. So let me share my screen. What I will try to do is basically I will try to give you a high-level explanation of what a CNN is. So it's a really complicated algorithm for someone who does not have previous knowledge of artificial intelligence. But I will try really briefly in the next 2 minutes to give you a high-level understanding of what is convolutional neural network and why is so big, really innovation in the artificial intelligence field. So as you can see here, this I don't want to overcomplicate it with slides or anything like this. As I said, I'm going to go really high level. This a completely random image that I found in the internet. I will try really briefly to explain you the CNN process. As you can see here, we have an image of a boat. You can think about any object that you want. You can cat, dog, all these are really common. So what is convolutional neural network? Convolutional neural network is an algorithm. So when we are talking about an algorithm, we are talking about different steps. The first step in this algorithm we are calling convolution. What is a convolution? Convolution is a process that we have defined some future maps. When we are talking about future map, we are talking about arrays. So think about a cat. If as a human, don't forget that artificial intelligence is inspired by the human and how the brain is working. So if you think about a cat, what is, in order to understand that it's a cat, what you will see as human? Probably you will want to see ears, eyes, maybe the mustache, anything, 4 legs, anything that you can help you understand that that this is a cat is this is our future maps. So future maps is an array of numbers, as you saw before of what Daniel was showing. Is we are playing with arrays. Every image before sorry let me clarify something. Every image is an array, is a 3D array with red, green and blue RGB colors. So it's a 3D array which every of cell of the array is representing pixel. So this is so our future map is going to be an array as well. So the convolutional process is that we are going to multiply this array that we have from an image, the 3D array that we have from the image, with an array that we have defined as it's going to be this feature. We are going to classify a cat, a cat's ear. The other feature will classify a cat's eyes. So our algorithm, we have defined, we are going to say to our algorithm that, you know, this array is going to represent the ears of the cat. So every time that I'm going to pass an image in my classifier, my algorithm is going to search for this for ears in an image. This is mainly the convolutional process. The result of this multiplication is going to be a bigger array, which is the array that will detect the ears and maybe the ear or the legs, the mustache, anything is calling future detector. The result is calling future map. Apologize about that. So the result is going to we are going to call it future map. This is our future map. So the future map is an array of that we have defined, that we have found the ears in our classifier. After this process, we have the pooling. Pooling, we have a lot of different ways of making pooling in CNN. It's the average pooling, it's the max pooling, is whatever you prefer and whatever is best for the algorithm, from the problem that you are working on. So, for example, we can say average pooling. Average pooling, we are using this pooling process for two reasons. Because after the multiplication we have an even bigger array. So what we want is to go to lower dimension, to squeeze our array, and also to not lose information. So with this pooling process, we are keeping the important information, but also we squeeze the array so we have a smaller array. And the second is because we want to have invariant in our image. Think about this. You have a lot of different cuts, like you can detect a ear on the top right corner or on the top left corner, whatever the image is. So we don't want to lose important information because the ears are in a different position. This problem is solved by the pooling process. And we are repeating this as many times as we believe it's best for our problem. Finally, we have this fully connected layer, which is just an artificial neural network. I'm not going to go deep in the artificial neural networks because it's a really huge process. I just want you, if you are curious about, a couple of weeks ago we had a speaker called Marius Katsakioris who went deeper on all the different neural networks that there are out there. It was a really nice and a long presentation, but I think that he gave a really good understanding of all the different neural networks that are out there. I suggest to you to go and have a look at this. The links are in our group chat, or I don't know if Ben has shared anywhere else. But think about this fully connected process. Think about it as just a classifier. So you have your features that it's going to be the ears, the legs, anything that you have in mind. Think about it that you are passing to an algorithm, and this algorithm processing and give you a result. And you can see here this pretty nice convolutional neural network. It says that the probability that this that you are watching here is 0.94% both. He has a 0.94% also that it's BERT, which is okay. The image maybe it's a little bit confusing, but I mean this is not good. But in any case, the output will be the classification. The probability of this object will be how much the probabilities that this is a cat, this image is a cat. In our case, because it's a binary classification problem, we will have just yes or no if it's fire or not. If you know about statistics, think about this as a linear regression. You are giving some in a 2D array, you are giving some points, and you have your linear regression which says on the left-hand side is it's true, on the right-hand side it's false. The artificial neural networks are a combination of a linear model plus an activation function. That's all for me. If you have any question, don't hesitate to ask it now. I know that's a lot of information to digest in a really short period of time, but I just wanted to give you a really brief explanation of what right now Daniel is going to present you as code. So you will see that you will have this conv2D function in Keras that is going to do this convolutional process. You will see that you have this average pooling function that is going to do this pooling process. And also the last part, if you can see here, we are calling dense layer. So in our case, as we said, we have a binary classification, so the output will be yes or no if it's a cat or not. So you are passing the image, you are doing the convolutional layer, you are doing the pooling layer. After you have this dense layer that, as we said, is just a classifier. It's going to give you, given the feature, is going to say, yes, this is a cat, no, this is not a cat. Any questions? Daniel, what do you think?
Any questions?
Okay, so it's all you from now. I think if you have any questions, don't hesitate. I mean, we can answer it later. If you have like anything come up, we are here for you. So like, yeah, Daniel, I'm going to stop sharing my screen. It's, yeah, go on.
Okay, so
Thanks. Thank you very much, guys.
thanks, Nick. So, right. So we're here. Can everyone? Oops, have I muted myself? Can you hear me?
Yeah, we can hear you.
Okay, cool. Perfect. Right. So that's it. So that was kind of an overview of the theory. These things called convolutional neural networks. It's a layered structure, and somehow the image is going through that layer. And at the end of it, it's going to say, it's a cat, it's not a cat. It's a boat, it's not a boat. It's a match. It's a burning. Well, it's a lit oven lighter. It's not a lit oven lighter. And this actual model is inspired by the visual cortex. So these studies go back to the 60s and then the 80s. Fukushima, a researcher from NHK, so let's say the BBC Japanese equivalent, was researching image, and that was his inspiration. These studies on the visual cortex of cats and how the image was processed as it went through the brain. So fast forward a few decades, here we are. And we have well-established libraries such as Keras and PyTorch, which you may have heard about. Could we have a show of hands of anyone who has heard of Keras and or PyTorch? So Keras, K-E-R-A-S, and PyTorch, P-Y-C-O-R-C-H. Sorry, PyTorch, P-Y-T-O-R-C-H. No one, no problem. So today is the day we hear about what Keras is. So we'll be using the Keras library to build this layered structure. So, and we start to say import TensorFlow as TF. So we're saying we'll use this library, but we'll just use a shorthand TF to refer to it. And from TensorFlow, import a bunch of Keras libraries. So a Keras is like a wrapper around TensorFlow. So many people used to complain, oh, TensorFlow is too complicated to use. And this Keras, which is a few years old now and well established, says, well, we're going to make it simpler. We're going to wrap it in code that's simpler to understand. So it says, in this case, it says import the Cypher 10, which is a data set that we won't be using. So I just forgot and left it here. And then import an image data generator, which we also won't be using. I forgot to leave it here. Import from Keras models, import sequential. We will be using this, and basically it's saying you're using the sequential model to create these layered models. So there are others. Sorry, you're using this API, application programming interface. You could be using others, but this is the one we're using here. It's called sequential. And then also from the layers, import tense, dropout, activation, and flatten. And we'll see what that is as we go along. Then from layers again, import conv2d, so convolution 2d, and average pooling 2d. So average pooling, Nick mentioned when he was showing his slides. And so here we load all the libraries we need. The next thing we do is say, well, let's declare a model let's create a model. So we call this function sequential, which we imported from Keras. And then we start to add layers to this sequential model. So we say, we're going to add a convolutional layer with 16 filters. So what this means is, remember we saw those feature maps, so those blue squares that were like stacked one behind the other. It's saying, give me 16 of those. And to create this, we're going to have a kernel size of 3 by 3. So this is the little square that was going over the image. So this is like the little box that's going to scan the image for features. We'll create me an activation. It's called ReLU. I'm not going to go over this. This is a bit kind of too high level to pick it up on the first session. But basically, this is the way that layer is going to decide what value is given, how it decides on that activation. So depending on how the numbers come out, what are you going to forward along to the next part of the network. That's what this activation is about. I'm not going to go over it this time. And then it says the shape, the input shape of this, so the actual image size that I'm expecting is this one here. That's a crucial bit, because if you turn up with an image that is of a different size, so let's say it's expecting this square 100 by 100 pixel size for image, and you put a different size here, it's going to complain about it, and then it's all broken, it won't work. So this is the catch. Everything else is fairly straightforward. So, and then it says, right, after you've added that convolutional layer, add me a pooling 2D layer. So I'm going to go over with a little square thing, I'm going to go over the image, and then depending on the size of that square, I'm going to pick like either the highest value, which would be max pooling, or the average value, which would be in this case of a pooling. And when we talk about values here, we're talking about pixel values. So we've seen that array, what it looks like. We have values for red, green, and blue. And in this case, it would say, okay, so what is the average value of this little pixel here? And it would say, well, the average value in that square. So for every pixel we're looking at is 100, right? That's the one we're going with. And then it says we're also going to add a dropout layer. This also is a bit of an advanced kind of topic for now, but it's basically saying, oh, by the way, we're also going to lose some of the neurons at this point. Not the neurons. We're going to forget some of these values at this point, just so to try. And this is also kind of a deep topic called, we want to break symmetry, but that's all I'm going to say. Let's not say anything else about dropouts because it's a bit confusing. Now, this next one, you say, oh, I've seen this already. We're doing exactly the same thing. We're adding a second layer, and then also with average pooling, except this time we're going to add 32 features. So it will be 32 of those squares lined up, one after the other. And the kernel size is going to be 3 by 3. So that's what happens next. After that, it says, right, this time we're going to add 64 filters. So same structure again, but this time we're going to have more squares. And if you remember the slide Nick showed, you might remember that on the first convolutional layer, there were less squares, but they were a little bit bigger. On the next one, there were more squares, they were a little bit smaller. On the next layer along, convolutional layer, there were a lot more and they were a lot smaller. And this is typical of the way convolutional neural networks are designed. And then here comes this flatten layer. So what is flatten? We import it up here. Basically what this does is it gets all these feature maps that are this long list of these squares that are stacked along the feature maps, and they all have these RGB values inside them. So it's an array. And what this flatten is saying, get everything that you have there on all those feature maps and just string it along in one long array. So unlike those arrays that we saw up here that had like 3 values, and oops, where are we? Here, image size, I lost it. But anyway, here, frame data. So here, what we had was a 3-dimensional array, which had our RGB values. So what that flatten function is, what that flatten layer is going to do is say, get all these numbers and just string them along an array with just a single dimensional array, and everything along that array. So that would be the flattened part of the convolutional network, also typical of this design. And then we can see that what follows here are 3 dense layers. So what we see, and it says, give me 250 units, which in this case are called neurons. I'll introduce some more jargon here. And it says, I'm going to use an activation value. I'm not going to go over it in detail. I kind of went over it briefly. And it's also saying we're going to use dropout. I'm not going to go over that. But basically what this is saying is all those values that you've picked up here, we're going to send them, every one of them. So it's going to be a fully, we're feeding all, this is going to be our input now. We finished all the bits that we're trying to extract features, and we're saying, right, now pass them on to this dense layer. So we have a bunch of neurons, so 156, and then we're going to have 128, and these layers are fully connected. So everything, all these units that are up here, these neurons, which we can see as like these round cells one next to the other, are connected to these 128, and then they're connected to these two down here. So, and then we're going to have a softmax activation function. I'm not going to go over this, but basically it's going to give us a probability. This is, of it being one class, it's going to give us two probabilities, in fact, which we'll see later on. And then it's also going to give us a model summary. So that's what this code is going to be. If we run the code, and please do so, if you're following on your own Google Colab, right at the end here, this model summary says, print me a summary, and it says, right, here's a summary. You have the layer types, you have the output shapes, and you have the number of parameters. So what are the parameters? The parameters are these weights. So if you think about a linear equation in the slope-intercept form, y equals mx plus b. So yx are our inputs, and m and b are our parameters. So if we wanted to find out, we look at a line and say, what's the line equation for that line? Basically, what our task there is to find the value of m and b, so slope and intercept. And then once we have that, we figure out the parameters, right? Those are the parameters for that line equation. These are parameters, so same thing, but a lot more complex, same principle. So we have a bunch of parameters here. So in this layer, we have 448. In the next convolutional layer, which is the actual size is smaller, but we have a lot more filters, as we have seen up here. So we've seen that in the first one, we have 16 kernels or filters, same thing, or they're kind of interchangeable, those two. Sorry, no, they're not. What they're saying about filters is feature maps. So here, in this context, feature means that we're going to have 16 feature maps, 32 feature maps, 64 feature maps. So what we're seeing is, as the size is decreasing, the number of, so as the size of the feature map is decreasing, the actual number of parameters is increasing. We have more, the size of the feature map is decreasing, but the number of feature maps is increasing. Remember the long list of squares at the end? So we have more parameters as in those further layers. And finally, in the fully connected layers, that's where we have the most of our parameters, because that's where most of the bits are connected to each other. Like these layers, so we have this flat layer connected to another flat layer, and every neuron is interconnected. That means there are lots of parameters there. And then the next dense layer, we have less, because there are less parameters. And finally, on the last one, which we only have an output of 2, we have the previous dense layer fully connected to 2. And then we can see, right, we have 128 here, we have 2 here, they're fully connected. So that means 128 times 2, that's the number of connections we have here. That's this figure. And so it's saying the total number of trainable parameters in this neural network is over 500,000. Remember, the total number of trainable parameters in a linear equation is 2. Well, actually it's 3, because if you look at the m as the slope as the x coefficient, there's actually a coefficient for y, but it's normalized to 1. So everything is divided by the value of the coefficient of y there. That becomes 1. And then, so it doesn't look like a coefficient when you just see y equals mx plus 3. So that really would have 3 parameters. This one has over 500,000. So it's a lot more complex than let's say a linear equation with 3 parameters. But essentially, it's doing the same thing. We're trying to approximate a function here. So if we ran that, we got this, and now we can finally train it. So now we run this line, history.fit, and yeah, history equals model.fit, the X and Y, the data, the images and the labels. We want the batch size to be 32. So when you're going over this, train the network with 32 images at a time. And epochs, train for a maximum of 100 epochs. Each epoch is when you go through all the training sets. So that would be one epoch. So we're saying go through the training set a maximum of 100 times and split the training data into 70% to train and 30% to validate. So 30% of the data the model won't actually see while it's training. Right. So if we click that play button, the model will start training. So remember, this is Keras running in the background, and it's training, saying, right, I've run it for one epoch, and the loss function that was defined. But did we define a loss function up here? Yes, we did. So the loss is part, I'm not going to go over this, but basically it's saying there's a loss function, and that's what's used in training to tell our model during the training how things are going. So if the loss is increasing, then so we say, no, things are not going very well here. So it says, right, let's try to go the other way. And the idea is we want to increase the loss. And typically, we want the accuracy to go up. And we see that very fast here, the accuracy reached 1. And I'm not going to go over the reason that today, but basically, it's the model is doing very well in this case. And is everyone running that training fitting our model okay? Could we have a show of hands? We're almost done way. We're overrunning a little bit. Cool. Ben Hinge, Ben Frost, yeah. Marina, are you managed to run that okay?
I do.
Yes.
Cool, perfect, fantastic. So all being well, we've reached 100 epochs and we have a loss of 1,000 of a unit and an accuracy of 1. Right. We'll go over this in future sessions, but basically it's saying your model is doing very well. And then when we ran this up here, we said fit the model and assign it in the output of this model.fit. So we created a model, which is this Keras sequential model, and we said use this method fit and so basically we're calling a function here, the fit function of this model class, and the output has been assigned history. So down here we're going to say, so if we click that play, it says what type is history, and it will say, well, history is of type TensorFlow ... history. So that's the type. What kind of keys have you got in history? And it says, oh, it's a dictionary, or it's a Python it's a dictionary. But anyway, what I'm saying, what kind of keys have you got in history? And it said 4 keys here: loss and accuracy, which were the training loss and accuracy values, and Vowel score loss and Vowel score accuracy, which are the testing losses and accuracies. Remembering that during training, we're looking at that 70% of data. During validation or testing, we're doing the 30% of the data. So, and then I go on to say, show me all the values that are kept in the loss key. So we have 4 keys, and I'm saying, just show me the ones you have in loss. And it says, these are the values you have. Scroll through that list, we see those values decrease. I'm just going to scroll, I'm going to close that now. And now what we're doing is we're going to save the model. I'm saying save that model to something called firemodel.h5. And here we're going to verify it with so if I click play there, it should be the model. And to verify that, we run list and L for list and H for human readable, firemodel.5, and it says, oh, these are the attributes of that file, read, write, execute. It belongs to the root user. It's the same with you. You're the root user on your virtual machine that you're running on Jupyter, your Jupyter notebook is running on in this Colab environment. The size of the file was 7.5 megabytes. It was the time it was created and the model name. Cool. So now we can actually, we have that, we can run a prediction. So we run that and we say, from map, oh, sorry, we're not going to run a prediction. We're going to say, show me the plots for accuracy and validation accuracy and accuracy and where's loss here? Oops. Okay, yeah, for accuracy and validation accuracy. So this is going through that history list that we looked above, and it's just plotting it, saying this is what happened over those 100 epochs. The validation was a bit all over the place. It was going up and down. I'm not going to go over what was doing that. And then we see that the training accuracy kind of steadily kept going up, and soon both were up at nearly 1 or close to 1. So very, very accurate both. And then we're saying, so that was the measure of the accuracy of the model. Next, we'll plot the training loss. So how did this loss function, which is also a measure of how well the algorithm is doing, is how that loss value, how did it vary as the training epochs went along? And it says, well, when it started, the loss was very high, but as the training progressed, the loss started dropping. So basically it's saying that our model, as these epochs are going along and we're training all the data, they're getting better and better at predicting the correct class. And then you can say, oops, there's some spikes here. So the training went really bad here, and then it came down again, and eventually by the 100th epoch, they had a very low loss. So the algorithm was predicting correctly what the correct class was. Cool. So now, finally, and a little bit late, sorry for running, we can actually say, and what I'm doing here is I'm just saying, oh, by the way, if that model was on disk, if you just downloaded the model off the internet and had it at this point, right, this I find really exciting. Imagine there are loads of public models out there. As long as you know what the input of that model is, you don't have to do any of this stuff we did. You just have to go out there, get that model, put it here, and says, import that model, let's start making predictions. I find this mind-blowing, and it's all happening. Anyway, so now finally we can run a prediction. And if we click that, it will say, right, the plot size is going to be 64. This is very important, remember, because we have to know what size the input was, because the model on its own does not know. It's just there waiting. It's just like this matrix, enormous, full of numbers waiting to be multiplied and added. And but it doesn't tell you explicitly what size the input has to be. So and then we go say, load this image, resize it. This is the important bit, adapt size. Show me the image as a sanity check. We're showing it down here. Convert the image type to float 32, which is also important. It has to be converted to float in this case, not an integer. It is a data type thing. I'm not going to go over it. And then, also very important, we also normalize the values of the pixels here, just as we did when we were training our model, when we were creating the data set. So we're basically giving the model the same normalized range between 0 and 1 for all these pixel values. And then we say, now go and predict. And then there's a bit we have to do here with the axis. I'm not going to go over it now, but it's also important in presenting it with the same data format. And then we say print the prediction, print the probability of no fire, print the probability of fire. And this is held in this prediction list. So remember, our model outputs 2 values. It has 2 neurons at the end. And what it's outputting are 2 probabilities. The sum then is going to be 1. So let's have a look down here. It says, right, the value of, so print prediction, and it printed the prediction. We see it's a list. It has 2 entries. One is very close to 0. So it's 1 point something something times 10 to the minus 5. The other is very close to 1. So it's 9 point, so very close to 1. So it's saying the probability of no fire is very close to 0. That's my prediction. The network is telling us. And the probability of fire is very close to 1. And there's the image it predicted. So moving on to the next image, this next section of code is doing exactly the same thing. So what we say here, so what we see is, here's the image, here's the list with the predictions. So the first one is a probability of no fire. The second one is a probability of fire. Remember our classes 0 and 1s, and it says the probability of fire in this case is 1. And the probability, sorry, of no fire, and the probability of fire is very close to 0. And the important bit to notice here is it's actually outputting a probability, so it's not telling us explicitly this is a fire, this is not a fire. It's down to us to actually draw the line and say, and this now, imagine us programmatically at this point, you're writing a phone app, and you're saying, right, I have my model, the prediction, here's the prediction on my phone. What do I do now? We have to set a threshold to say, if the prediction is about not above 90% of fire, I'm going to say this is a fire, I'm going to sound an alarm, I'm going to call the fire brigade, whatever the app is doing. But that is your decision as a system designer, so to speak. It's not down to the network. The network just produces the numbers as it is here. Obviously, you know, if you put it into a robot, it could well call the fire brigade and perhaps even operate fire extinguishers. But as things stand from hereafter, we would have to make a decision ourselves. So sorry for overrunning by 12 minutes. We do have a follow-up session next week. So bring your own data set. So if you'd like to bring cats and dogs or anything, that's what next week's session is about. And I'd like to hand it over to Ben. Thanking everyone for your presence. So Ben.
Before Ben, you know, if you guys are interested, you can even build like, you know, a classifier to, you know, to detect if it's yourself or not. So like, be creative with that. If you are interested in this, it's you can do a lot of different stuff. They are pretty we have pretty nice, cool stuff that you can detect or classify. That's this, Sir Ben. You go on.
It's fine. Yeah, really powerful algorithms there. Yeah, thank you, Daniel, for showing us that and going through the workshop. It was really interesting for me, and I'm sure it was for lots of other people as well. If you do have any questions, let us know now. But otherwise, we will wrap up. As Daniel said, we have a session next week where you can bring your own data, or we will have some data sets there if you don't have any data to bring yourself, and we'll run through some of these algorithms with you, so you can get hands-on experience on how they work. If you have any questions about that, you can sort of ask us then and there as you're going through the data. So I will wrap up for today then. Thank you everyone for coming. Loads of links in the chat. So give you a couple seconds to save those if you'd like them. I'll just copy the website link again, because if you'd like to sign up for the society and keep up to date with next week events, then you can do that. Okay, thank you for coming, everyone. Thank you, Daniel, and see you later.
Cool.
Bye-bye.
Thank you. Bye-bye.